equals 0, you put the first equation there, and you set value of 0. By changing variables s are the variables you're solving. The remaining equations, you add them here as constraints. And we're doing that in, those of you who are taking the control class, that's what we have been doing in the control class just now. So in this case, I just have one equation, so it's very simple. So my one equation is going to be the objective. So highlight this, and click what is the calculated function that should be 0. What's the calculated function that should be 0? That minus 0.17, right? Alternatively, you can click here, and then click here. Careful, if you, I copied the second one does have the equation, okay? This has the equation. Wait a minute, it added the sign. I had already typed so. Okay, click on it. So $d$1 is what you should say. That's what I have my objective. Instead of maximum minimum, value of. The default is 0, which is what I want it to be. And what am I going to be changing? The final temperature. So you can click this if you want and select the final temperature. That's how we set it up for just solving one equation for one unknown. How are we doing? All right. And then we click solve. Oh yeah, let's have the abomination, although I know the tensor has to be positive, and in this case it won't make a difference. I'll uncheck it. Solve. Found the solution? It didn't give me exactly 0. Why didn't it give me exactly 0? It has a default accuracy for convergence. I can go and make it more accurate if I want it. If you go back, okay, you can save that, but no, okay. So go back to solver. If you go to options, you can see the constraint precision, and all the qualities are constraints. So that's why the error came to be 10 to the minus 8. It allowed 10 to the minus 8 error in satisfying the equation. So if I put more zeros here, I'll reduce the 10 to the minus 8. Put a few more zeros, click OK, and solve again. Solve. And what do you see now? 0. Okay. Everybody clear? Taylor back there clear? Taylor here clear? Taylor, are you okay? All right. So now, that answers your question about the homework?
Yes, it does.
Okay. All right. I will do just, I'm selecting just important parts of the first 5 chapters of your text. This is all review. There's one last thing I will select, and then I'll move chapter 6, which I will cover thoroughly, because again, everything in chapter 6 we'll have to be using from now on. And instead of repeating the same derivations, I'll tell you just how else we derived it in chapter 6. Exactly, then I'll explain. So, ideal gas is a very important limiting case. We're going to be writing software for the Penn-Robinson calculations. And how you calculate quantities, I think you probably covered excess, the word excess property. Basically, you calculate the difference from the ideal gas. So what we have to be doing, we always have to be calculating the ideal gas case. Often, when you calculate something going from state 1 to state 2, and let's say it's a temperature pressure situation, let's say here's temperature, here is pressure, you'll be making your calculations in that, yes?
That's called a departure, correct?
Oh, that's the wrong thing.
Yeah, the excess is when you have.
Yes, you're right. You're absolutely right, Jamie. Jamie's right. All right. So you are following typically a path that will go through pressure to 0, which is the ideal gas part of the path. Yeah, I used the wrong thing. So being able to calculate the ideal gas path is going to be critical for everything we're going to be doing. And if you do temperature volume, at what volume do we have ideal gas behavior? Pressure 0, you have ideal gas behavior. At what volume? Infinity, correct. So if it's TP, this path, if it's TV, and we are from 1 to 2, we would go from 1 to infinity volume, ideal gas path here, and going to 2. So the last thing I want to do before abandoning the earlier chapters is calculation for ideal gas. Well, obviously, ideal gas enthalpy is the integral of Cp star dt. So for ideal gas, we need to be doing ideal gas enthalpy and entropy. So, of course, ideal gas.
Are we done with our computers for today?
Yeah, we're done with computers for today. No more computers for today. Okay? And H depends only on temperature. And of course, U would be with Cp star. How about entropy? Entropy of ideal gas doesn't depend only on temperature. You have to have two state variables to specify entropy. Can be temperature, the common ones are temperature and pressure, or in some cases you want to use temperature and volume. So let's find the expressions both for temperature and pressure and temperature and volume. So one of the equations that we discussed last time is that dH is equal TdS, and underscore means what? Per mole, molar quantity. Plus VdP. And for ideal gas, dH is Cp star dt. So combining the two follows that ds is equal this minus that divided by t. So I have 1 over t times dH, but I write dH as Cp star dt. And moving this to the other side, I will have minus v underscore over t dt. Okay? Ideal gas means obeys ideal gas law, which is, so that means that V molar over T that I have there is equal to R over the pressure. So if we put it there, we have that ds gives the dependence of entropy on temperature and pressure. And as the gas constant, because Cp star is only a function of temperature, okay, you don't have to consider here a path, and you can integrate directly. So, and let me say from Difference.
dp over t.
Did I miss something?
No, I'm asking him actually.
Huh?
Is that dp over p?
Yes.
Banana?
Yeah,
Okay.
dp over p. Anybody else? Okay. So, if you integrate it from reference temperature, you get that. In fact, let me regain my board. So S at any temperature and pressure is going to be as reference. I'll put this as reference plus integral of Cp star of T over T dt from T reference to T. Normally I would have to have a path from T reference, P reference to TP. Okay? But because this part only depends on temperature and this part only on pressure, whatever path I take, I'll still end up with those two integrals. Doesn't make any difference. What is the integral of dp over p? It's ln, right? dp over p is the same as d ln p. So that is, well, you don't want me to write directly. So it's ln p reference, ln p of minus ln p reference, which of course difference of ln's is the ratio, so ln p over p reference. So this is an equation we're going to be using a few times. And if we want to work with changes in volume, in molar volume, some problems this might be more convenient. Then we'll have an alternative derivation. Then I want to work with Cv star with du. If you are working with pressure, you're using H. If you're working with volume, you want to use U. So remember that du is dds minus vdp. And du is what? For ideal gas, Cp star dt. So I'll do exactly the same thing, the analogous thing I did with temperature and pressure. So now you see it will give me ds as a function of temperature. Okay. Oh, sorry guys. PdV here. Yeah. That's PdV. PdP is plus VdP is the dH. Okay, please correct. So, you see here I have ds, dt, dv gives me the dependence with temperature and volume. So, as before, ds is going to be equal to substitute du with Cv star dt, so you get Cv star dt over dt over t. And then you get plus moving into the other side, P over T dV. But what is P over T? Now, you have PV equals RT. So P over V, P over T, so equals R over T. Putting it together, we have ds equals Cv star dt over t plus now r dv over v or dl and v. So integrating it again from a reference. Again, this is only a function of temperature. This is constant. So again, whatever path you consider, it will be just this integral for temperature and this integral for volume. So you get that S at temperature any molar volume minus the reference is going to be integral of Cv star dt over t, the reference to t, in this case plus r ln of the volume over the reference. Okay, so these are the equations of how entropy changes if we have ideal gas. Any questions? Yes?
How would we obtain entropy reference, NT references? So is that going to be 0 or is that?
No, it's not going to be 0, even for species that have 0 heat or formation. Tables or something, and usually also references cancel out in calculations.
True.
So
Okay.
you can leave it as reference and then it will cancel out.
See what happens later.
Yeah. Okay. That concludes what I wanted to cover for chapter 3, chapter 6. And now it's time to do some necessary math, including, I'll remind you of the derivation of the Maxwell equations. Okay? Anybody needs more time? Juan, you okay?
Yeah.
All right, good. Okay, so we have 8 state variables. 8 common state variables. Which are temperature, pressure, molar, if I use molar quantity, molar volume, molar entropy, internal energy, enthalpy, Helmholtz, and Gibbs. For any pure single-phase system, giving values for any two specifies all the others. That means I can express any of them as a function of any two others. With the exception I mentioned earlier in the class of the two limiting cases, ideal gas and incompressible liquid, in which case temperature and enthalpy or internal energy for ideal gas, all those three are really one variable. So specifying any of those two doesn't specify anything of the others. And similarly, for the incompressible liquid case, density or molar volume is independent of pressure, only a function of temperature. So in that case, V molar and temperature is not given two specifications, it's given only one specification. So that means, what I wrote here means that any state variable can be expressed as a function of two others. So if you want, you can write U as a function of S and